So let's solve the following differential equation. Let's say we have a second derivative of x with respect to time is equal to sine of 2x, or 2t. Okay? And let's have an initial condition. X at pi is equal to 0, and x prime at pi is equal to 1. So the function that we get when we evaluate it at pi, we should get 0. The first derivative of the answer we get when we evaluate it at pi should be equal to 1. So this is a pretty simple looking differential equation. It doesn't go crazy off the board. The first thing you need to know, or to look at, but when we get into a lot of solution techniques, it's going to kind of overwhelm you a little bit. And because there's a lot of different ways to attack a problem. My advice to you is, when you first look at a problem, okay, the first thing you should look and say to yourself is, can I just integrate this equation to get the answer? Just like we did in volume 1 of differential equations. We did some problems that were really easy. We could just do sort of integrate to get the answer. Well, when we look at this, we have a second derivative by itself, and on the right-hand side, we have a pure function of time. So when you think about it, the first derivative, dx dt, is going to really be equal to the integral of this whole thing. So when we integrate this, we're going to get the first derivative. In other words, when you take the integral of a second derivative, you're going to get a first derivative. You integrate the right-hand side, you're just going to be integrating sine of 2t dt. So really what you're doing here is because you have only one derivative on one side, and because you have pure function of time on the other side, then you're allowed to integrate both sides of a differential equation. So integrating the left is going to give you a first derivative. Integrating the right, we have yet to do. When we get the answer, we're only going to know what the first derivative is equal to. We integrate it again to recover x of t. So it's kind of the thing you learned from Calculus 1. Integrals are opposites of derivatives. Here we have a second derivative. We know what it's equal to. So if we integrate 2 times, we're going to recover the original function with some constants of integration stuck at the end, which we're going to get rid of the constants with our initial conditions. We've been doing that in the other part of the course also. So the reason this is allowed, the reason that it's possible, is because we have one derivative on one side and we have a pure function of time on the other side. If you have more than one derivative over here, like maybe you have third derivative, second derivative, and a first derivative over here, you're not going to be able to just integrate that. And so I think we've shown through the last section and the section before that, that in general the equations can get complicated enough where simple integration is not going to work. But always ask yourself as a first step, can I integrate? Okay. The next thing I want to say before we go any further, because what we're going to do next is integrate this, is notice that this is linear. We have a second derivative. The function of time in front is just a constant. The only other thing on the other side of the equal sign is a pure function of time. So really this is e of t. This is my forcing function. It's a pure function of time sitting on the other side of the equal sign. This part, it's super simple in this case, but it describes whatever system I'm studying. This part describes how I'm pushing. So I'm pushing with some sort of sinusoidal, I say pushing, thinking about a spring system. It's easy for me to think of it that way, but it could be a circuit, could be fluid flow, could be pressure, could be whatever I'm forcing the system with. So for now, don't worry too much about that. Let's just go ahead and integrate this guy and see what we get. Now, a lot of you probably already know what the answer to this integral is, but if you want to show all of your work, you would do a quick substitution. So u is equal to 2t, and du is going to be equal to 2 times dt, just taking the derivative of this guy, and then solving this guy for du, so I'm going to have, or I should say dt, is equal to 1/2 du. The reason I want to solve it for dt is because I want to plug it in here. So I'll have the integral of sine, let me go ahead and take that off, sine of u, because u is now equal to 2t. dt I've just found is 1/2 du. So now I have an integral I can solve. It's all in terms of du. So let me go ahead and pull this out. Let me rewrite this. dx dt is equal to, we pull it out, 1/2. 1/2 comes out of the integral. What is the integral of sine? The integral of sine is negative cosine. So write it as negative cosine of u. Right? Now that is the integral. And you can write plus constant of integration, no problem. All right, now let's finish it off. We'll go ahead and finish it off by saying dx dt is equal to, we'll take the negative and stick it out in front of the 1/2, cosine of u, which is 2t. 2t plus some constant of integration. Now, like I know a lot of you guys are pretty good at integration by now, you might look at this and say, well, okay, integral of sine's negative cosine, so I'm going to get this. The 1/2 comes from taking the derivative of the inside, but you have to remember that it's 1 over the derivative of the inside. So whatever little mental tricks you like to do to integrate something like that, great. I like to show all my work so I don't make any mistakes. This is the answer. If you get the same answer by another means, that's fine. But notice what we found. We've integrated the function one time. We have recovered the first derivative, but that's not really the total answer. We want to find out what x of t is. So we need to integrate again. So if we integrate both sides again, x of t, which is really what we're trying to find, is going to be equal to the integral of negative 1/2 cosine 2t plus a constant. Make sure you understand that. If I integrate the left-hand side, I'm integrating both sides is what I'm doing. If I integrate the left-hand side, I'm going to recover the function, x of t. If I integrate the right-hand side, I just leave it like this because I haven't actually done the integration yet. So I'm integrating both sides with respect to time. So here I have the same kind of thing going on. I need to integrate a cosine that has something wrapped up in it. So you can do it however you like. I'm going to show all my work. So u is equal to 2t, du is equal to 2 times dt, and dt is equal to 1/2 du. So now I've got my substitution ready to go. So I'm going to have integral, actually, just to make it a little bit easier, I can pull the negative 1/2 out if I want, like this. Integral cosine of u, so I'm going to put u here, plus a constant. Don't forget the constant integration. Okay, this is what I'm integrating. But dt is equal to what I found it to be here, 1/2 du. So, simple integral. I'm going to pull this 1/2 over here, which is going to make negative 1/4. And what is the integral of cosine? Integral of cosine is just sine. So I'm going to have sine of u plus, what is the integral of a constant? Any constant that you have, whether it's 4, 9, 15, whatever, I'm just going to have my constant times time. And you should be able to remember that back from your calculus. So whatever number you have, if it were plus 5 here, then it would be 5t. Well, c is just a constant, so I'm going to make it c times t. All right, but I've done another integration, so I have yet another constant of integration, so I'm going to call it d. In your books, you know, a lot of books might call their first constant of integration c1, the next one c2, the next one c3, c4, c5. That's cool, that's fine. Do whatever you want to do. But I find that I make less mistakes if I choose different letters by and large, because C looks a whole lot different than D. And also it helps on the video here, because if I put too many subscripts, it's going to be kind of lost. So what we have done is we have found x of t. It's a negative 1/4 sine of 2t. Actually, we have to plug in back for u. So x of t is equal to negative 1/4 times the sine of u we define to be 2t, so we'll put 2t back in here, plus c times t plus d. Okay? Now let me go ahead and circle this, because this is not the total answer. Notice that we had initial conditions up there, so we haven't solved anything for initial conditions, but we've gotten pretty darn far in our solution, because this is the solution to the equation minus the initial condition. So it's got almost all the information there. It just doesn't incorporate what we have started the system at. So let me go ahead and rewrite this over here, because I want to point a few really important things out. X of t is equal to negative 1/4 times the sine of 2t plus c times t plus d. So here we go. Now I told you on a previous board that all of these linear equations, they always yield a solution of the form c times h of t plus p of t. This was what we called a particular solution, particular to our problem with our forcing function in place. This was a solution that was basically as a result of if we had solved this guy with the big fat 0 here, making it homogeneous. We put them together, particular and homogeneous solutions, and it forms the whole solution. You might not see that, you probably don't see that by looking at here, but it's staring at you right in the face, and I really want to take some time to point it out to you. Okay, I'll just tell you right now that these two terms here, C times T plus D, this is what we're calling in my definition below CH of T. So it's this part right here. This guy out front, this is what I'm really calling P of T, the particular solution. And I think, so I guess what I'm trying to say overall is that this answer does fit the general form, but you may look at that and say, well, how does he know that? You know, I don't really understand how he's figuring that out. Well, if you think about it for a second, what would happen if I took this equation, the original one that we started with, and I put a 0 here? If I took out my E of t, changed the equation, made it homogeneous by sticking a 0 here, then I would have second derivative of x is equal to 0. How would I solve it? Well, I would solve it by doing exactly what I did here. I would integrate 2 times. The only difference is I would have 0 in this integral. So if you can use your imagination, I'm not going to solve it again, but if you have a 0 here, what's the integral of 0? Well, the integral of 0 is just a constant, c. So this would be 0 here plus constant, right? And then so I have this constant of integration. So this dx dt would just be constant. I wouldn't have this cosine here. I just have constant here. Then if I integrate again, I'm going to integrate c when I do this integral down here, because this would be 0. I'm going to be integrating this constant. So when I integrate just this constant down here, I'm going to have c times t plus d, which is giving me this part here. So again, this is gone. I integrate the constant by itself. I'm going to get c times t plus d because I have a new constant of integration when I do the second integral down there. So by and large, I guess what I'm trying to tell you is if this was a homogeneous equation, I would integrate 2 times, and what I would get in the end result would only be ct plus d, where c and d are constants of integration. And that is going to be the case, ladies and gentlemen, for every equation when you make it homogeneous. When you put a 0 on the right-hand side and you start integrating like that, you're just going to get a bunch of functions. In this case, you know, we have a function of t here, but you're going to have constants in front of every term because every time you integrate, you're just going to get a new constant of integration over and over again, like what we've done here. So if we put a 0 here, we get ct plus d. That is reflected in our answer. We didn't specifically integrate that. We didn't specifically have to do it. It just falls out as a result of the math, okay? So file that away. Our solution that we got involved a solution to the homogeneous version of this differential equation. Extremely important that you understand that. We didn't try to solve the homogeneous equation. We just got that part of the solution as a result of doing the solution, you know, of the whole darn thing. And so we get that. All right, what's the second part of this guy here? This is what we call a particular solution. Again, we didn't try to find a particular solution. We didn't try to get this guy. It just falls out as a natural result of doing the solution technique. This guy, which I'm telling you is equal to this term here, P of t over here, is equal to the negative 1/4 sine 2t. Whatever's left over outside of this is going to be the particular solution. It is a solution that comes about only because of our forcing function being present, okay? So to prove that to yourself, and the reason we call it a particular solution is what I'm telling you is that this function by itself is a solution to this differential equation. It's not the whole solution set because we've got these other terms over here. That's going to generate more and more solutions because of these constants here. But this little part right by itself does satisfy our original differential equation. And I want to prove that to you because it's really important. So let's go and look at this. Our original differential equation is d squared x dt squared is equal to sine of 2t. And what I want to show you is that this little term we're calling a particular solution is by itself a solution to what we started with. Even though you didn't try to find it, it just happens to be that way. Okay, so let's go and do that. We need to take 2 derivatives if we're going to say that x of t is equal to this. So we're going to say x of t, we're just going to say, is equal to negative 1/4 sine of 2t. And we want to plug it in here. We need to take 2 derivatives. So x prime of t, how do we take the derivative of this? Derivative of sine is cosine. So we're going to have negative 1/4 times the derivative of this is 2 times cosine of 2t. So at the end of the day, x prime of t is going to be equal to negative 1/2 cosine 2t. That's the answer to the first derivative, negative 1/2 cosine 2t. Let me change colors really quickly. And let me find x double prime of t. So we're taking the derivative again, basically. So what we're going to have here is negative 1/2 times the derivative of the inside, 2, times, what is the derivative of cosine? It's negative sine of 2t. So at the end of the day, what I'm going to have here is negative times negative gives me positive. This gives me 1. So really, I'm just going to have sine of 2t. Sine of 2t, and that's all I have. So I took the second derivative of this particular solution, and look what I got, sine of 2t, which is exactly equal to the right-hand side. So make sure you really understand this. We did the solution technique. We get the answer just by simple integration. I'm telling you that part of what you got is really just because of the solving the homogeneous version, which you kind of did without realizing it, yielding this. The other part is really a honest to goodness particular solution. When you plug it back in, it satisfies the differential equation. That's what we mean by when we say it's a particular solution. To prove it to you, we take two derivatives of this guy, we get sine of 2t, which is exactly equal to the right-hand side. So I'm proving to you that what we got really and truly is a particular solution. I'm not going to do that ever again. I just wanted to do it once to show you that it's true. What I'm really wanting you to pull away from this is that this is a pretty simple solution method. We're just doing integration. But later on down the road, when we do much more complicated solution techniques and you get an answer, it's always going to basically be broken out into a particular solution and a homogeneous solution. And we're going to exploit that fact later on in solution techniques down the road. You really need to know that the sum of these two things really and truly is the total solution. So one more time, I'll say it again. This is a particular solution that's a result of the particular forcing function we had. Notice this, if we change the forcing function, p of t is going to be different because this integral is going to all be different, and then this is going to be different. So this is a result of our forcing function. This guy is kind of the generic part of the solution that's just as a result of how we've actually set up our system in our differential equation. This is just one solution. This represents an infinite number of solutions because we have two constants here. It's really important for you to know. When you put them together, you get a solution space that has an infinite number of solutions. C could be 9, D could be 10, C could be negative 5, D could be 24. So this is particular, this is homogeneous, and when you put them together, you get an infinity number of solutions, okay? Which is the total solution space. Now, how do you get away from having in real life, you don't have an infinite number of solutions, right? How do you nail it down to the one solution that you want? Well, you do that because you specify your initial conditions. And your initial conditions are going to lock down C and D, and that's going to be your total solution for your particular problem on your particular day. When you pull the spring back this far and let it go, that's going to govern your solution. So what we need to do is solve this equation given our initial conditions. And our initial conditions, just to remind you, was x at pi is equal to 0 and x prime at pi is equal to 1. Those are your two initial conditions. So what we need to do is plug these guys in. And just to make it absolutely clear, I'm going to write them over again. So x of t is equal to negative 1/4 sine of 2t plus c times t plus d. This is the total solution. We just need to find the constants of integration. So here we have x of t. This is the solution that we were seeking. And we're going to need the first derivative. So let's go ahead and find out what that first derivative is. We've already kind of done that before. So what we're going to have, when we take the derivative of this, we're going to get a cosine. This 2 is going to come out, so we're going to have negative 1/2 cosine 2 times t. The derivative of this is c, and the derivative of d is 0. So this is the first derivative that we seek. Next, we need to plug in our initial conditions. So we plug in at x prime of pi. And you should really always start at your highest derivative. So we put 1 is equal to negative 1/2 times cosine of 2 pi, because t is equal to pi, plus c. And ultimately, we're trying to find these constants here. So we have 1 is equal to, what is cosine 2 pi? That's just 1. So we have 1/2 plus constant. So when we move the 1/2 over here, we'll have 1 1/2, which is 3/2. So C is equal to 3/2. So this is one of the constants that we seek there. The second one is going to be found by using the other initial conditions. So what we'll have is, I'll just write it over here, x of t is equal to -1/4 sine 2t plus c times t plus d. So here we'll plug in our initial condition x at pi is equal to 0, put a 0 here, -1/4 sine of 2 times pi, because t is equal to pi in our initial condition, plus c times pi, because t is equal to pi, plus d. So we basically plug in everything we know, and what we get, 0 is going to be equal to, what is sine of 2 pi? Sine of 2 pi is 0, so this whole term goes to 0, plus c pi plus d. But we know what c is. C is equal to 3/2. So what we're going to have here is 0 is equal to 3/2 pi plus d. So d is equal to -3/2 pi. D is equal to -3/2 pi. So we found both constants. We have c is equal to 3/2, d is equal to -3/2 pi, and we have everything we need to write our total solution down. So x of t is equal to -1/4 times the sine of 2t plus c times t, but c is 3/2, so 3/2 t plus d at the end. D is equal to -3/2 pi, so I'll write -3/2 pi. So this is the total solution, is going to be -1/4 sine 2t plus 3/2 t minus 3/2 pi. And this is the actual solution to the non-homogeneous version, which means we have a forcing function in there. So I want to go through it a little bit because I took a few detours along the way to make sure you understood a few things. We started with this differential equation. The first thing you should ask yourself is, can we integrate it? We have a pure derivative, second derivative, but still, it's pure derivative on one side, pure function of time on the other. We integrate once and we recover the first derivative, which is given here. We integrate again and we recover x of t. So this is really the general solution, is really what we call it, the general solution of the differential equation. And I took time to point out to you that this general solution includes a solution to the homogeneous version when the function, forcing function 0, plus a particular solution. Okay, and I proved that if we take this particular solution, that when you plug it in, it really and truly is a solution. So that was sort of a little bit of a detour to show you that. Once we have this general solution, we just plug in our initial conditions. We have to take the first derivative in order to apply this initial condition. We do that and we solve for c, constant c. We use the other equation and plug in this guy to find d, and then we stick those constants back in. Notice that there are no constants anywhere in here. This is one and only one solution, and it corresponds to our initial conditions and the system that we set up. So it's a really good problem. It's not a very hard problem from a calculus point of view. The next problem that we're going to do is not going to be really hard from a calculus point of view either, but it's very important that when you look at a second order and higher equation, first try to see, can you integrate it? If you can, do it. And I also wanted to make sure you really understand how the solution is split up into the particular and the homogeneous parts. Okay, our next problem is going to be a little bit more complicated. We're going to have a fourth derivative of x with respect to time, and that's going to be equal to 3t minus 1. So you have a fourth derivative here on one side by itself, nothing else. On the other side, you have a pure function of time. So the first thing you should do is say, can I integrate this? And obviously, if you had lots of derivatives added together over there, you wouldn't be able to do it. But here, since you've got this guy by itself, pure function of time and an easy function of time, you are going to be able to integrate it. So that's what we're going to do. Now, this particular problem has some initial conditions. X at 0 is equal to x prime at 0 is equal to x double prime at 0, which is equal to, you guessed it, 0. Lots of problems write it that way. What this means is x at time t0 is equal to 0. First derivative at time 0 is 0. Second derivative at time 0 is also 0. It makes the end calculations a little bit easier to have a problem like that, but it still gets the point across, so we're going to go with that. So what we're going to do is integrate it, but before we do that, I just want to point out to you that this is obviously linear, and it's non-homogeneous because we have something on the right-hand side other than 0. This is what we typically call this E of t function, the forcing function. This is how we're pushing on the system, feeding it with energy. And this guy is describing whatever we've built that we're modeling. Now these cases are super easy, but as far as simplicity goes over here on the left-hand side, but you get the general idea. So what we're going to do is really a bunch of integration. So let's go ahead and set ourselves up for that. If this is a fourth derivative, then the third derivative, d3x dt to the third power, the third derivative, is just going to be the integral of this guy, 3t minus 1 dt. So don't forget, we've done something very legal. We've just integrated both sides. Integral of this side is going to recover the next derivative up. Integral of this side we have yet to do. All right? So let's go ahead and do that. What is the integral of this on the right-hand side? Well, this is super easy. We'll have 3 halves t squared plus integral of this is t plus a constant of integration. Okay, c. So we have 3 halves t squared plus t from this integral plus that guy, and that is equal to the third derivative, right? So we have to keep on integrating to make any progress. So the second derivative, d squared x dt squared, is going to be the integral of what we just got here. So I'm going to write it out again so nobody's lost. 3 halves t squared plus t plus a constant dt. So the second derivative is the integral of what we just got back, which is the third derivative there. Okay, so this is going to equal, it's probably better to do it on the next line here. So we'll do integral of this polynomial. 3 halves is the constant out in front, over, raise this one more, which is 3t cubed, plus integral of this 1/2 t squared, plus integral of this c times t. But don't forget, you have another constant of integration you have to tack on to the end. So we're getting a little bit longer each time. We started out with something easy, we got something a little bit longer, now we've got something a little bit longer, and you can guess as we keep integrating, we're going to get more and more and more terms piling on. Now let's simplify this a little bit. So we'll have d squared x, or I should say the second derivative of x with respect to time, is equal to, well, if we kind of imagine this over 1 and flip it over and multiply it, the 3's are going to cancel. So I'm going to have 1/2 t cubed plus 1/2 t squared plus c times t plus d. That's what I'm going to really have. 1/2 t cubed plus 1/2 t squared plus c times t plus d. All right, so we found the second derivative. Now we have to keep on going and doing it again. Okay, so let's integrate this guy. The first derivative, dx dt, is going to be the integral of what we just found here, which is 1/2 t cubed plus 1/2 t squared plus c times t plus d. We have to integrate this dt. All right, but again, it's just another polynomial, so it's not that big of a deal. So we have out here 1/2 over 1 plus this is going to give me 4. This guy plus 1/2, 1 plus the exponent is 3. Whoops, I forgot something here. I have this guy, and then I have t to the power of 4, and then I have 1/2 over this guy, which is 3. 1 plus that is 3, and then a t to the third power plus, how do you integrate this? This is just a number, don't forget that, so you can do c over 2t squared for this guy, integral of this plus d times t, because this is just a constant, so if it were 5, it'd be 5t, so here it's dt, plus e. Now you see why I do different letters for my constants, because I can see constant, constant, constant. If I have C1, C2, C3, it gets really complicated. Okay, so let's do a little bit of simplification. dx dt is equal to, whenever I simplify this guy, I flip it up and multiply it, what I'm going to get is 1/8 t to the fourth power plus, when I multiply this guy, 2 times 3 is 6, so I have 1/6 t to the third plus over here, everything else after that's going to remain the same. C over 2 t squared plus d times t plus e. Okay, so I found the first derivative, so all I got to do is do this one more time, and then I will get the answer. So let me go over here and rewrite this as final answer, or getting close to the final one. So x of t is going to be the integral of what I've just found down there. So I'm going to rewrite it. 1/8 t to the 4th power plus 1/6 t to the 3rd power plus c over 2 t squared plus dt plus e integrated over dt. So getting a little bit tired here, doing it over and over and over again, but this is the kind of thing you'll have in your test. So integrate this again. What you're going to have is 1/8 over 1 plus this is going to give me 5 t to the 5th plus 1/6 over the 1 plus this is going to give me 4. And then I'm going to have t to the 4th power plus this guy, c over 2 over 1 plus this is 3 t cubed plus d half t squared plus e t plus f. Because this is my last constant. Make sure you understand that. I kind of went fast at the end. This guy is just d over 2 t squared. Integral of e is just e times t. That's the end of it. And then I have another constant of integration. So notice how many constants I have. 1, 2, 3, 4. Notice it's a 4th order differential equation. So you're always going to have the same number of constants as you do the order of your differential equation. Now I'm fully aware that this does not look very pretty, so I'm going to tidy it up. So we'll have x of t equal to, when we do this, flip it over and multiply, I'll have 1 over 40 t to the 5th power plus this guy, when I multiply, it's 1 over 24 t to the 4th power plus this guy is going to be c over 6 t to the 3rd power plus this guy is going to just remain the same, d over 2 t squared plus e times t plus f. So here's what we call the general solution. It is an infinite set of solutions because you have all these constants. We're gonna fix that in a minute by solving for those constants. But right now, let's just make sure we've got the right thing. We've got 1 over 40th t to the 5th plus 1 over 24 t 4th plus c over 6 t cubed, d over 2 t squared, e times t, and then f. Now, what do you think is going to be the homogeneous part of the solution and the particular part of the solution? The way to figure it out is the homogeneous part is going to be everything including all the constants, basically. So this is what we call CH of t, and this is a shorthand thing. C means constant, H of t means everything else, the functions of time that we have. So it's not literally telling you it's just the constant c. It's basically the sum of the terms that include all of my constants times, you know, these little functions I have. These are this is basically the solution to the homogeneous version of my original equation. Everything else left over is going to be p of t, which is the particular solution. So in other words, if I were to go back here to my original equation and take e of t and remove it and put 0 in its place, making it homogeneous, I would integrate this guy 4 times on the right-hand side, and I would end up exactly with this right here. Okay? And that's basically what we mean when we say it's the solution corresponding to the homogeneous equation. This is a particular solution. It means that by itself, this is a solution to this equation. And we proved that in the last guy, but just suffice to say, if I take this function, these guys together being one function, and I take 4 derivatives of it, I'm going to recover what's on the right-hand side because it is a particular solution. So you take the particular solution, you stick it with the homogeneous solution, you put them together, you get an infinite set of solutions that covers everything. It covers the part that involves the homogeneous part, the function, and the system that we have designed and built and modeled. It covers the forcing function that we have. And then, of course, we have to use our initial conditions to find our constants. So we are going to do that right now. To find our initial conditions. So what we're going to do is realize actually that we've actually already taken these derivatives really when you look at it, because we started with a 4th derivative, we have a 3rd derivative, we have a 2nd derivative, we have a 1st derivative. So really we have everything that we really need to evaluate our initial conditions right here on the board. So let's do that right here. Our initial conditions are x at 0 is equal to x prime at 0 is equal to x double prime at 0, and it's all equal to 0. So always start with the highest initial condition you have, the highest derivative initial condition that you have to proceed. So we need the second derivative. Our second derivative is given by this right here. So what we need to do is plug in t is equal to 0 here, because t is equal to 0, and set it equal to 0. So let's go ahead and write that down. What we'll have, let me just go ahead and write x double prime down, just so we're all on the same page. X double prime of t is equal to 1/2 t cubed plus 1/2 t squared plus c times t plus d. And what we need to do is plug in this initial condition here. So at time 0, x of t is equal to 0. So this will be 1/2 times 0 cubed plus 1/2 times 0 squared plus c times 0 plus d. So d is equal to 0. So one of our constants of integration that we have for this particular guy, for these initial conditions, is d is equal to 0. So that's important. Now, in order to make progress, we need to go backwards looking at the first derivative. We know what the first derivative is. We've used that right here. All right. So what we're going to have here, the first derivative, we've used quite a bit, is 1/8 t to the 4th power plus 1/6 t to the 3rd power plus c over 2t squared plus d times t plus e. That is the first derivative. Now we have to plug in. It's all equal to 0, so we'll have 0 is equal to, and just to make it a little bit easier on the eyes, this is going to be plugging in 0, this is going to be plugging in 0, this is going to be plugging in 0, this is going to be plugging in 0. So just to kind of make sure you know, it's going to be 0 plus 0 plus 0 plus 0, 0, 0, 0, 0 plus e. So what does this mean? It means e is equal to 0. Okay, so we're getting there. So we have d is equal to 0 and e is equal to 0. Now I just noticed one thing. There's actually one more initial condition here. X triple prime of 0 is equal to 0. I just neglected to write that on the board. So you really should always have as many initial conditions as you do the order in your differential equation. So here's 1, 2, 3, 4 initial conditions. So we've already found d and e. And what we're going to do now is go and try to find, well, we'll go and backtrack for a second and go up to our third derivative and try to find c. So let's go over here and rewrite that as follows. So what we have here, we need to find the third derivative. The third derivative is 3/2 t squared plus t plus c. So the third derivative, x triple prime of t, is equal to 3/2 t squared plus 3/2 t squared plus t plus c plus t plus c. This is the third derivative. And what we're trying to evaluate here is triple prime of 0 is equal to 0. So it's going to be 0 on the left-hand side. You plug in 0 here, you get 0 and 0. So you have 0 plus 0 plus c. So c is equal to 0. So that's one of our third constants. And then finally, our last initial condition, we've done triple prime is equal to 0, double prime is equal to 0, single prime is equal to 0. Now we need to look at x of 0 is equal to 0. So the solution that we found, x of t is equal to this guy right here. We have to plug in everything we know. So x of t is equal to 1 over 40 t to the 5th plus 1 over 24 t to the 4th plus c over 6 t cubed plus d over 2 t squared plus e times t plus f. Lots of writing, but it's pretty easy actually because it's all equal to 0. 0 here. T is equal to 0, so you're going to have 0 here. T is equal to 0, so you have 0 here. Here, t is equal to 0, but the constant c is also equal to 0, so you're going to have 0. Here, t is equal to 0, but we found d is equal to 0, so d is 0 there. E is equal to 0 and t is equal to 0, so this is 0 plus f. So in this particular case, all of the constants of integration happen to work out to be equal to 0. So when that's the case, we look at our general solution and we stick this constant equal to 0, this constant equal to 0, this constant equal to 0, and this constant equal to 0. Basically, that wipes out that half of the equation. So the specific solution for this particular set of initial conditions, x of t is equal to 1 over 40 t to the 5th power plus 1 over 24 t to the 4th power. And that's the answer. 1 over 40 t to the 5th power plus 1 over 24 t to the 4th power. So this is the solution with our initial conditions. Now I want to go over it again. I took a few detours through that here. So we have a differential equation. It's a fourth derivative is equal to a pure function of time over here. The initial conditions, when I originally wrote the problem down, I neglected to write this one. You always have to have as many initial conditions as you do orders in your derivative. So really, when you watch this lesson, just realize that there's really a third derivative equal to 0 on top of everything else. So what we do is we integrate both sides. We get the third derivative here. We integrate that again. We get the second derivative. We integrate that again. We get the first derivative. And when we integrate the first derivative, we get x of t, which is what we want. So this is the general solution to the whole enchilada. And we showed you that part of it is due to the homogeneous solution, and part of it is due to the particular solution. And that's just the way all these things are going to work out. I didn't prove it to you, I'm just telling you that this is the case, and we talked about that earlier. So now we have to apply our initial conditions. The way I worked the problem, I started out with these guys, but really you should start with the highest derivative initial condition that you have. It's going to be easier to solve. So you look at the triple derivative of t is equal to this. This is what we found from earlier, and we plug in our initial condition. We stick at 0 and t is equal to 0. We find that the constant c is also equal to 0. And then we go and look at the second derivative, which we found to be this guy. In this case, we know c is equal to 0, and all of these time t's are equal to 0, so that wipes out everything over here. Left is equal to 0, so we find that d is equal to 0. Same process finds that e is equal to 0, and the same process when we look at the original x of t, setting that equal to 0, all of these terms, for one reason or another, basically drop out to 0, so f is equal to 0. So using the initial conditions, we found c, d, e, and f, all four of our conditions are equal to 0. That only happens because of the extremely simple initial conditions for this problem. If it were anything other than equal to 0, then you would have numbers for all of these c, d, and e, and f, and then you would stick them in their spot, and that would be your solution with the initial conditions here. But the point of the guy is, to really understand, to take home, is the most important thing is that linear differential equations are of this form, and if you have one derivative on one side and a pure function of time on the other side, you can just integrate to find the answer. Doing the integration is a different story. How easy or how hard that is depending on what you have. Notice that in this case it was a simple polynomial, but it still took us a few boards to get it all done right. So imagine if you had sines and cosines over there, integrating them over and over again can lead to a lot of error. So make sure and check your work on that. Most important thing to pull out of it is the solutions that we get really are going to be of this form. And the reason I keep picking on that and keep putting that right back in front of you, that the solutions we get are a mixture of the homogeneous solution to the homogeneous version of the equation plus a particular solution, is the following. I've kind of saved the punchline for the end, because as we go on further, we're going to learn about this in the next several sections. A lot of times what we're going to do to solve more complicated differential equations of second order and higher is we're going to pretend that they're homogeneous first. So in other words, this is the original equation. It's much more complicated with this e of t here. But in more complicated solution methods that we'll learn later on, it's going to be common to just pretend this isn't here and put a 0 there. Solve for the homogeneous version, right? Then you're going to get what's going to amount to this part of it. And then you're going to use that to help you find this part of it. That is why it's so important, because the theorems in your books have proven over hundreds of years of studying differential equations is that if you can find the solution to the homogeneous part of that equation, and if you can find the particular solution, if you wedge them together and add them together, they will describe the complete solution space we call the general solution of the differential equation. Then you lock your constants down with their initial conditions. So later on down the road, when we get complicated things that are non-homogeneous, we're just going to make them homogeneous, solve that guy, and then we're going to use those answers to help us find the other part of the solutions. Because we know that if we can just find them by any means that we have, we can wedge them together and create the real true solution to the whole thing. That's why it's so important to know how these things are really constructed. If you have one and you have the other and you add them together, if you can find them by any means you can, then you can have the general solution. So that kind of delves into the theory of differential equations. I'm not proving that to you. I'm not showing with a big proof that this is always going to be the case. This is something for your book, and actually it's probably beyond the scope of most of the books. It's really way into the theory of how people have proven the differential equations work. Our job is to build upon that knowledge, get our feet wet with real solution methods, understand how to apply the things that people have learned over the years so that we can then take those tools and build things like airplanes and spaceships. And of course, I'm thinking from an engineering point of view, but if you're a math major, then you would take that knowledge and go and further the mathematical theory and use those tools to build upon it. So I'm Jason. I hope you've learned something here. Mainly, I just wanted to kind of get these points across so that when we go to the sections down the road, you won't be blindsided by what I'm saying here, and you'll really have it ingrained in your head so that when we get to the further, more challenging solution techniques, they won't seem so complicated and they won't seem so foreign. Learn anything at mathandscience.com.